Good morning. It's the physics video lecture. Physics 105B video lecture 19. I brought some demonstrations today. We're talking about rigid body motion, moments of inertia, things like that. So I'll start with the all-time classic moment of inertia sticks. So these were made here on campus. John Beckman made them a few years ago. And you see they have the same length, but there are aluminum pieces, and on the one stick, the aluminum pieces are mounted at the ends, and the other one, they're mounted in the middle. Okay, and there's a lot more density in this aluminum here than in the wood. So, and you know, because of the way they're made here, the symmetry of them, you can see that it's the same amount of aluminum and the same amount of wood. But you have to take these in your hand and give them a twist, because this one's really easy to twist, and this one here, much more difficult. You really feel the difference. Okay, it's the same thing I was telling you about the ruler the other day. So whenever you're back in the physics department, go ahead and ask to try these out, and anything else we have back in the cabinet there. So here, there's your moment of inertia demonstration. And this one here is interesting as well. So we have these two wheels, and I can throw them on the scale and show that they have the same mass, and you can see they have the same radius. They've been drilled out differently, so that this wheel here has the holes drilled out on the outside, and this one has the holes drilled out on the inside. And if it's the same amount of material, you'd have the same mass, but you're going to have different moments of inertia. Okay, so now you guys just have to ask yourselves which one is going to win a race rolling down the ramp here. I'm not going to say anything. Okay, which one has a greater, which one has a lower moment of inertia? So you want to think about that. I'm going to see if red wins or if blue wins. Red is closer to you guys. On your marks, get set, go. We have a definite winner. Blue was the winner. So think about that. And finally, I brought a couple of pendula. We're going to talk about the physical pendulum. We know all about the simple pendulum because it's a mass at the bottom and a length of string or massless rod or something. Here we have a pretty much uniform mass distribution, but it's going to do the same thing. Okay, simple pendulum, but this time it's the physical pendulum, and we'll have to use Newton's laws with torque and moment of inertia to characterize it properly. This one here is just a lot of fun. It's amazing. We could have assigned the double pendulum Lagrangian. Maybe we still will, who knows? Okay. So this is the double pendulum, and you can see how it's made. This one has equal lengths and equal masses essentially. Whereas if you want to formulate this in general, you give it two different lengths and two different masses. Okay, so this is a limiting case of that. And you know, it'll have small oscillations, and you can see there are a couple of modes there. So we're talking about normal modes and stuff. There's our small oscillations. It would take us a lot of work just to figure this one out, right? But there's a lot more going on than just this. If you put enough energy into this thing, it's just endlessly complicated and very interesting as well. So Dr. Vitali has a program in which he can integrate the Lagrangian equations of motion here and show all manner of these phenomena in simulations. But yeah, you can see it's really rich compared to the small oscillations world. That's fully nonlinear dynamics. Okay, good. I'll get rid of these, and we're back to our discussion of rigid body motion. Okay. Okay, so we have to do the physics of these things. Oh, I think I know what I'm going to do. Bring back the both boards. There we go. Okay, pretty high tech. So, rigid body motion and the dynamics, and we were doing it for a fixed axis, and what I just showed you was essentially for a fixed axis of rotation, fixed axis of rotation. So let's just call this rigid body motion fixed axis. Actually, we're going to extend that a bit to rolling motion since we just saw that. Fundamentally, that's also the fixed axis because the direction of the axis of rotation stays the same. So what do we have so far? Let's just remind ourselves of this formalism. This is stuff we learned in Physics 4a. We have angle, we have omega equals d theta dt, we have alpha equals d omega dt. Writing those down in shorthand. And you may remember there are kinematic equations that go with this that are just like the 1D kinematics with constant acceleration. But then if we go from kinematics to dynamics, we have L equals I omega, and then we have to know that the moment of inertia is m sub I, L sub I squared as defined last time. And we have torque is equal to, I could write I alpha or I d squared theta dt squared. I'll write it that way because we had just come to that Newton's law, and we have the moment of inertia as well. So we have to do a little bit more with the moment of inertia. And I had mentioned we're going to do the parallel axis theorem. So we'll do that, and then we'll be able to do some dynamical problems. Just to complete our list, we also had the rotational kinetic energy was a half I omega squared. We seem to have the full analogy to our linear motion here in the simple rotational world. Okay, so what I want to talk about next is more of the moment of inertia. So moment of inertia and parallel axis theorem. So I'll start this off with a homework problem. We want the moment of inertia of the uniform sphere. And you've probably seen this before, 2/5 m r squared. Hope I got that right. But we want to integrate it up using the spherical polar coordinates this time, because we gave another problem along those lines with the center of mass problem. So integrate using spherical polar coordinates. Yeah, this is something we need, this integration technique for what we're going to be doing later. So that's a good problem, and I can discuss it in other connections and in the current connection as well. Let's go ahead and set that up. Again, we have I is equal to integral dm times this L squared. So we have to orient ourselves. Let's say we've got our sphere in x y, z, there's angle theta. We have to get a little mass element, okay? So we need a volume element in spherical polar coordinates. So the dm is going to be density d volume, and then an L squared. So as far as the density goes, it will be total mass divided by 4/3 pi radius cubed. And then we need the d volume in spherical polar coordinates. R squared sine theta dr d theta d phi. So yeah, make sure you get this volume element in spherical polar coordinates, and yeah, I want you guys to look that up and find it and figure it out. When we do the transformation formula, we're going to review all that stuff and do it from scratch. Okay, what's our L squared? Our L squared, since we're going to let z be the axis of rotation, is going to be x squared plus y squared. But what's the x squared plus y squared going to be? X squared plus y squared will be r squared. Actually, no, not r squared. It will be you'll have an r squared here times the rest of your x and y in terms of spherical polar coordinates. We had them up on the board last time. Okay. And your integrations are going to be dr 0 to r, d phi 0 to 2 pi, and d theta 0 to pi as defined here. So yeah, you can work around with that a bit. Turns into a reasonably easy problem. And make sure you get the official result. And when we want to talk about, instead of spheres, ellipsoids, we're going to learn how to do a coordinate transformation to go from a sphere to an ellipsoid. Okay, so yeah, we definitely want to have the sphere in our repertoire. Good. So that's a good exercise. And we will use this this example in a moment as well. So okay, I'm going to erase this. This is how you're going to get set up and get moving on that problem. So now let's look at the parallel axis theorem. And we have enough definition right up above here. So here's what we imagine. We've got some rigid body, and we put the origin right in the center of mass. Okay, the origin in the center of mass. I'm going to go ahead and call this x, y, z, because I'm mostly concerned with the x-axis. But in that regard, okay, the moment of inertia subcenter of mass, which is sum of mi li squared. In this case, it's the mi, and since we're rotating about the y-axis, it's x squared plus z squared, each one with a sub I. Okay, so that's the definition, because that's the distance from the y-axis, x squared plus z squared, distance squared from y-axis. Okay, so there is our moment of inertia, and of course you could convert this to an integral the way we're doing up there. And we're rotating about the y-axis. Now suppose we have a parallel axis, a parallel coordinate system here. I'm going to make sure that I'm just taking an axis parallel, so my origins are lined up, and I have a distance d right here between those two axes. And I'm going to call this the y prime axis. And I want to know what is the moment of inertia with respect respect to this new axis here? Equals question mark. So that's our question. Now we have enough room here. We'll just do the definition. We have I prime is equal to sum of m sub I and the L sub I prime squared. Let's even write that out. We're gonna skip no steps here. L sub I prime squared sum over m sub I. And this L sub I prime squared is the x prime, which is the x sub I plus d. Okay, that's my x prime. X sub I prime is x sub I plus d. That's how I set it up there. My z sub I prime is the same as my original z sub I. So this is z sub I prime squared. So we're going to expand this thing out. Maybe I should have left more room, okay. We're going to expand this out, so we've got sum over m sub I. And let's see what we all have here. We have xi squared plus 2xid plus d squared plus z sub I squared under the sum there. And we're going to bring that up here. That equals sum over m sub I, and I'm going to take the xi squared plus zi squared, and then I have plus sum over m sub I, and I have 2 times xi times d. Well, the d and the 2 are constant, so plus 2d sum over m sub I xi. And I'm left with this plus d squared sum over m sub I. Now the cross term, you'll notice that's the numerator of the center of mass coordinate of x center of mass. Okay. So this equals 0, comma, because we put the origin at the center of mass, right? Origin at center of mass. Yeah, that cross term is gone, and I'll write this now and put it in the box for us. So we have m total mass d squared plus this is the original center of mass moment of inertia plus I sub center of mass. Okay, so that's the parallel axis theorem. You just take the center of mass moment of inertia and then add the point mass moment of inertia. If you had a point mass rotating around this axis right here. Okay, so this is a great result. I'll explain, we can do any number of simple examples. One thing you might look at is last time I measured the moment of inertia about this axis here in the center of the rod and here at the very end. And you can verify my two formulas as fulfilling the center of mass, fulfilling the parallel axis theorem as well. Okay. But I want to leave this up here for a moment, so I'll erase this calculation. So the utility of this theorem is really substantial. So suppose you have this sphere here, and you do, there it is, okay. X, Y, Z, rotating around its Z axis here. and we have I, this over to this side, we have I center of mass equal to the 2/5 m r squared. Well, suppose you wanted to know its moment of inertia around this slightly displaced axis. Well, that's trivial now, right? We've got the center of mass, moment of inertia, and then we're just going to add total mass times whatever this distance is squared. So that's trivial, but suppose you actually had to do the integral with respect to that red axis. Okay, that's not trivial. That integral would be comparatively nightmarish. So that's actually an insight to keep there in your bag of integration tricks. That could even come in handy sometime. Definitely can in the context of dynamics. That you use that parallel axis theorem. You can even just look at it as an integration trick. This type of integral would be pretty much impossible, and yet it would be trite with the parallel axis theorem. Okay, good. Let's see how we're doing time-wise here. Okay, very good. So now we want to do a couple of applications of this. And let's see, we can start anywhere. We're going to start with the physical pendulum. Yeah, I'll use this side of the board. We'll start with the physical pendulum, then we'll do some discussion of rolling motion. Yeah. Parallel axis, I'll just put I center of mass plus md squared. So we have that there too. Okay, so the physical pendulum, this is an important application. Because every pendulum that you build is a physical pendulum, even if you make it as ideal as possible. So we'll do the analysis of that. The idea is that, say we just had a stick of wood or something, and there's the axis, and we want to have that oscillate back and forth. So there's our axis of rotation, and the angle is going to be here, phi, this is the down direction. It's going to be the angle phi. And we have rotation, as I said, about this axis, but there's a center of mass. I should label this. I'll make a slightly bigger picture. Yeah. So there we have our object. There's the axis of rotation. There's vertical. Here's our angle phi. Or are we using theta? We'll use theta. Here's our angle theta. And where I put this little star is where the center of mass is located. And then I'll take a distance d is from the center of mass to the axis of rotation. So yeah, we know that the net gravitational force, the weight, is acting at the center of mass. We have a theorem for that. And so if we want to write tau equals I d squared theta dt squared as our Newton's law, we'll see that we have a clockwise, or in this case, more pertinently, a restoring torque. So we get the minus sign mg d sine of theta. Okay. That's just this mg, and there's our lever arm, as it were, d sine theta. Okay, so my mg d sine theta is equal to I theta double dot, and then we have second derivative equals minus mg divided by I. Good. We could, of course, also write down a Lagrangian for this thing right here. Okay. We actually have expressions for kinetic energy, everything else. So, or Lagrangian. Okay. Lagrangian would be L equals T minus U. L is equal to 1/2 I d theta dt squared minus negative mg d cosine of theta. Okay. So either way, it's good to remind ourselves we have this other formalism. Just like I said with what we were doing in Physics 4a. So both of these, in fact, this one, leave room in your notes. You know, the Euler-Lagrange equations, dl, not so fast. Euler-Lagrange equations, time derivative of dl d theta dot minus dl d theta equals 0. Right? That had better give us this equation as well. Okay, so where do we go with this now? In the case of this formalism, we recognize what we have to do. We have to expand the cosine to second order. That'll give us the theta squared over 2. If we want to do the small oscillations Lagrangian. If we write this equation out, we're actually going to get this, and we'll have to do the small angle approximation in the sine. So let's do that next, small angle approximation. Yeah, doing these side by side is good. You know, if I don't assign it as a homework assignment, leave room there to just knock this thing out. It's really basic in the Lagrangian formula. We're going to arrive at the same thing here. So I'm just going to write here next, small angle approximation. So theta much less than 1, that's what we say. Theta double dot is equal to minus mg d over I, and sine theta just goes as theta to first approximation. So there's our equation of motion, and you're supposed to immediately recognize this as theta of t equals all right, theta max cosine of omega t plus some alpha. Okay, supposed to recognize that immediately. 2 time derivatives minus this. And what is our omega? Omega is equal to the square root of mgd divided by I. Okay. So whichever way you approach it, this way or this way, Euler-Lagrange is going to give you that. And then it's that second derivative minus a constant times the quantity itself. Immediately we get this. You know, in fact, from the small oscillations Lagrangian, you would be able to go straight to this step, okay, based on what we've been doing so far. You wouldn't even have to take the Euler-Lagrange equations. You take this thing, expand it, small oscillations style, theta squared over 2, and you should immediately just come up with this. So let's continue to analyze this. And we're interested in the limiting case. So mgd over I, we have I is equal to md squared plus I sub center of mass. Well, we don't know the center of mass of any old object. Okay. So omega is going to be equal to m times g times d divided by, so we got square root, md squared plus I sub center of mass. For a point mass, the moment of inertia vanishes. Okay. So for a point mass, this vanishes, and then what do we get? Omega is equal to the root of g divided by d. And period is equal to 2 pi root d divided by g. Okay. So yeah, this is the formula that we know very well. Okay. The period of the pendulum. With the frequency in the period of the pendulum. Okay. So here's a great homework idea. Consider, so here's a homework problem. Consider this disk M and R, and it's attached you got a disk of mass M and R. We'll let this be a massless rod. Attached to a massless rod, length L. So we have R here, and we have L here. And this is a pendulum. It's like on a clock or something. Okay, it's a pendulum. Length L. So what we want to do is find period T, okay, and then find L such that T is minimized. This is a great problem. Okay. You can make it more complicated if it were a massive rod, but it's a massless rod, and you can adjust the length of this rod to give you a minimum of the period. Because you can see if you take the rod out to infinity, of course the period is maximized or is increasing. But also if you take the rod to 0, the period's going to increase as well. And you'll see that when you do the analysis. It's an interesting problem here. So in fact, when you find that when you want to minimize the period, you express, instead of omega, express the inverse of this as the period, and you take a derivative. So that's an interesting problem. An interesting physical pendulum problem. And the physical application of that, how much time do we have here? Oh, excellent. So the physical application, you could say, is this: if you found the length of the rod that minimizes the period with respect to, this disc-shaped bob, then you would also find the length of the system that is most impervious to thermal expansion or contraction. If you have a grandfather clock, thermal expansion and contraction actually affect the timekeeping properties. So if you're at a local minimum or maximum, then the expansion and contraction of L affects the period minimally because of that. Okay, so that just brings a little other physics into the mix. Good, so that's a great problem. That's the physical pendulum. This one you really want to know, okay? It's just an elementary application beyond just the simple pendulum, and yet there's a lot of rich physics in there. Also, before we leave that, maybe I will write down the inverse expression there, simply because it's actually a little easier to think about. Okay, so now we have md squared over, so we have md squared plus I sub center of mass over mgd. Because we can really look at the correction term now. So md squared over mgd is just d over g, what we just had. So let's put the 2 pi there, sorry. 2 pi root g d over g, as before. And then we have this I center of mass over mgd. I'll put this in parentheses because say you had a pendulum with some little spherical pendulum bob, then this is how you would generate your corrections, okay, to the ideal pendulum. If this term here is small with respect to d over g, then of course you can expand this thing and get correction terms. Okay. So I'll just put this as a note. Expand to get correction terms. You can also turn the argument around. You can carefully measure periods of a pendulum and then get a handle on all of these properties. For one thing, you can use it to determine G, but if you think you know G well enough, you can actually, using the pendulum, get some of the mass distribution properties of your object. Okay. So rigid body motion, for that reason, is really rich. You can do the dynamics in both directions. Okay. You can predict what you're going to see. You can take what you see in order to understand, the structure of this thing, what you can't see. Maybe it has a hidden compartment inside, okay? Maybe it isn't, maybe the mass isn't distributed the way you think it is. Okay, how much time do we have? We have a lot more topics. We'll do a little bit more. We'll wrap it up with the rolling race and leave it at that. Okay, we'll go ahead and erase this stuff. We want to spend a little time talking about rolling motion. Because then next time we'll actually come in with the more general theory. This was all just review, but this review has some interesting stuff in it as well. So rolling is something I just demonstrated with the downhill race a moment ago. And what we can do is say that kinetic energy has a translational and a rotational part. And we actually have a theorem for this going back to point mechanics, where we were able to break up the kinetic energy into an internal and a center of mass kinetic energy. Okay, so if we talk about the rigid body, then the rotational kinetic energy is the internal kinetic energy, because the rotation is about the center of mass. Okay? So we immediately inherit this expression here, and with what we're working on, we have the 1/2 mv squared plus the 1/2 I omega squared. So a translational and rotational. Translational, that's right, translation, rotation. But this refers to the center of mass, and rotation. In our earlier point mechanics discussion, that would have been the internal kinetic energy. In fact, we obtained it that way because we just had something rotating about a fixed point. Okay, so that's fully legit. And we're going to use as our example the rolling demo that we just did. So we just have things rolling down an incline. To give it some suspense, we were racing, but we just now have an object that is rotating about an axis of rotation. So I'll even say it's down here at point A and goes to point B, has an elevation x, gravity pointing down as usual. And we could either settle Lagrangian up, but in this, or get equations of motion, or we could just go straight to the energy expression. So energy is going to be conserved, and we would have 1/2 mv squared plus 1/2 I omega squared plus, actually, let's keep this simpler. We're starting from rest. I was going to write out the conservation law, but we're starting from rest, so let's just say we have potential energy at point A, and when we roll out at point B, we have 1/2 mv squared plus 1/2 I omega squared, and we've taken care of all our potential energy. Because it's rolling motion, we can say with V is equal to omega R. So that'll allow us to solve this one too. So we're just going to solve for the speed. And we're making a substitution, omega equals V divided by R. So we'll do this in two steps. We have mgh equals 1/2 mv squared plus 1/2 I, and then V squared over R squared. And we'll solve for the V squared. We have I divided by R squared plus M equals 2 mgh. And we're going to divide both sides by I'll solve for V right away. We're going to divide both sides by M, so we're going to end up with 2gh divided by the root 1 plus I divided by mr squared. Okay, so this expression is good to contemplate for a moment. Okay, because you can really see the effect of the moment of inertia on the rolling speed. I'll circle it right here. With zero moment of inertia, say something is sliding, then it's just the root 2gh that you get from the law of free fall and you get from the general conservation of energy. The greater the moment of inertia, the greater your denominator and the slower you're going to be going. So you're putting more energy. This was a purely energy calculation. You're just putting more energy into the rotational term. And you can see this I is being measured against mr squared, which would just be the rotational inertia of a mass, right, at distance r. So yeah, you can get some good insight out of this, and if you were trying to engineer a wheel that rolls the fastest, you can see you put all of the mass in the center in order to make I, the moment of inertia, as small as possible. That's how you would win races. Okay, so that was rolling, which we finally got around to talking about. And I think we'll leave it there. Next time we start with the more general theory of rigid body motion. See you next time.